Welcome. This is the material of Chapter 7, Correlation Models of the book Elements of Financial Risk Management by Peter Christoffersen. The goal in this chapter is to model the correlation between assets. This correlation changes over time, as we can see in this graph. We review first the constant correlation model, that is the base for portfolio variance and value at risk computation. Next, we introduce the concept of exposure mapping. And finally, we're going to see three models of dynamic conditional correlation named DCC models. In the case of portfolios, the value at risk and expected shortfall formulas are the same than in the case of stock returns that are multivariately normally distributed. The variable that we're going to tackle in this chapter is the volatility of the portfolio. In here, we're going to have the correlations. What is the return of a portfolio and the volatility of a portfolio? The return of a portfolio is a sum of the returns of the individual securities multiplied by the weights that each of the securities has in the portfolio. The portfolio variance covariance is going to be also a weighted average now of the covariances of the assets. Or in this more general way, we can write it as the weighted sum of the asset I and asset J. This is going to be the volatility, and then here we have the correlation. So far what we have done is models for the volatility, such as GARCH or the realized variance. And now what we're going to do is models for the correlation between asset I and asset J. The most important feature of this correlation models is that it's going to make our correlation time varying, to change over time. The general formula for the portfolio variance covariance matrix is the multiplication of the variance covariance multiplied by the weights transpose, and here the weights. In the two asset case, you would write the variance of the portfolio. This would be the vector of the weights transposed at the beginning and at the end, and then in the middle we would have the variance covariance matrix. However, the variance covariance matrix is as large as the number of assets that we have in our portfolio. So if we have, let's say, 100 assets, then you're going to have a 100 by 100 variance covariance matrix. That's about 5,000 covariances. The first methodology that we cover is exposure mapping. The exposure mapping, what it's going to do is going to reduce the dimensionality problem when you have too many assets in your portfolio. So the first thing is you have the portfolio returns and you regress it against the beta and the market return. In this case, the variance of the portfolio is a function of the beta squared and the variance of the market plus some error. Hence, we can approximate the variance of the portfolio with beta squared, the variance of the market. If you write the return of a portfolio as a function of several factors, as in this case, such as the market factor, the Fama fringe factors, and the momentum factor, then the variance of the portfolio is a function of the betas and the variance covariance matrix of the factors. So let's say if you have, as in this case, 10 factors, then this variance covariance matrix is only going to be a 10 by 10 matrix. So imagine you reduce from 100 by 100 to just a 10 by 10. Since correlations are time varying, we need models for correlation. Correlation is defined as the covariance over the individual variances. So if this individual variances change over time, hence the correlation is going to change over time. There's a nice property of standardized returns. Remember that Z is the standardized stock return, which is return over its volatility. A very important property is that the expectation of Zi, Zj is going to be equal to the correlation of I and J. Therefore, we will work in this chapter with standardized returns and we're going to model their correlation. The first correlation model that we're going to cover is the exponential smoother. This model is equivalent to the risk metrics model for variances. It models the variable Qij, which is a pseudo correlation. Qij for tomorrow is a function of lambda and the multiplication of the standardized returns ij and the previous day Qij. Qij is not the correlation itself since it can take values above 1 or below -1. Therefore, we need to normalize this Qij variable to obtain a correlation that is between -1 and +1. This is the formula of the normalization. We have Qij, and then we have Qii and Qjj. So these correlations between II and Jj should be equal to 1, but the problem is that they're not going to be exactly equal to 1. That's why we have to normalize. The second correlation model is equivalent to the Garch model for variances. It's a mean-reverting model for correlations. The model mean-reverts to the sample correlation rho ij, which is the sample correlation of the standardized returns. Hence, this model is going to depend on two parameters, alpha and beta, and then rho ij is going to be this constant that we define with the sample correlation. As before, we need to normalize Qij to obtain our correlation between I and j. In the two-asset case, for the mean-reverting correlation, we can write it as follows. So this is a matrix form to write it. Our Q11, Q12, Q22. So tomorrow correlation is going to depend on these three parameters. It's going also to depend on the correlation of rho bar between asset 1 and 2 and alpha and beta. Again, to obtain the correlations between asset I and asset j, we need to normalize our Q12 variable. The last model for dynamic correlations is the asymmetric DCC model. So far, we have considered that two positive returns have exactly the same impact on correlation than two negative returns. So if Zi, Zj are positive, or if both are negative, they have exactly the same impact on correlation. Now, on market crashes, we know that correlations increase. Hence, we want to have two negative returns impact more correlation than two positive returns. For this reason, we're going to define this variable eta for each stock. Eta is equal to the standardized return if the return is negative, or 0 if the return is positive. The sign of gamma is going to be positive to model that stylized fact. Hence, what we're going to have here is whenever we have two negative returns, so we are going to have eta taking a non-zero value. This is going to end up being positive times a positive number. It's going to make our correlation being positive. This gamma is equivalent to the leverage effect for variances, so it's kind of modeling that leverage effect for correlations. Now we turn to the DCC model estimation. We use the bivariate normal distribution. On the x-axis, we're going to have the standardized returns. So this is the x-axis. So we are going to have the standardized returns for asset Z1. And the y-axis, we're going to have the standardized returns for asset Z2. Notice that it goes from -3 to 3 in both cases. This surface up here is going to show the probability of Z1, Z2. So as this correlation, as the rho changes, then the surface is also going to change, which means that the joint probability distribution changes or is a function of the correlation. The DCC model estimation is formally done with the bivariate normal quasi-maximum likelihood estimation. This function represents the log of the bivariate normal distribution. The inputs are the standardized returns Z1 and Z2 and their correlations. The changing parameter in this likelihood is the correlation, which we already saw is a function of Q12, Q11, and Q22 by this process of normalization. In turn, the Q11, Q12, and Q22 in the case of the exponential smoother are a function of lambda. So we're going to maximize the likelihood function by changing the parameter lambda. In the case of the mean-reverting Garch, we're going to have a more extensive model that is going to be a function of alpha and beta, and is going to have a mean-reverting correlation rho 1, 2 bar, that is the correlation between Z1 and Z2. In this case, we estimate two parameters, alpha and beta. The estimation for large systems with n stocks involves a function, a likelihood function that is a little bit more complicated. In here, we have the correlation matrix, and the bars indicate that this is the determinant of the correlation matrix. So if we want to implement this, we'll have to take at each step the inverse of the correlation matrix and the determinant of the correlation matrix. This makes this computation computationally demanding and actually very inaccurate and unstable. So for this reason, we write this function as a sum of the bivariate likelihoods. So if you have 100 variables, you have about 5,000 correlations, so we will have to write the 5,000 pairs as a sum of each pair. In that case, again, the rho is going to be a function of the q's, and the q is a function of, let's say, alpha and beta. Now notice that in this case, if we do this for 10 assets or 100 assets, the alpha and beta is exactly the same across all assets. So we would still be maximizing as a function of only two parameters, two that are going to be alpha and beta. There's not going to be one for each individual pair. So in conclusion, in this chapter we have introduced models for correlation, since correlation changes over time. We first reviewed the constant correlation approach, where VAR is computed as a function of the portfolio volatility and the inverse normal. The portfolio volatility is written as a function of the weights, the volatilities, and the correlation. And this is the correlation that we tackled in this chapter. We did it in two ways. First, we introduced mapping exposure to a market factor or to a set of factors. And then we introduced dynamic conditional correlation. And there we introduced three models: the risk matrix correlation, the Garch mean reverting correlation, and the asymmetric correlation.